The old saying goes, and now for something completely different. Yeah, I like to break up the course and just do a complete change of lanes here and start talking about unit testing. You might hear the term test-driven development as well, which is just basically the opposite of the testing. Instead of creating the code and testing it, you actually define the test first, and then you write the code to make sure it passes the test, and then you follow the cycle that way around. Anyway, unit testing, one way or another, we're going to get there. All right, so here's a question. When do you test your software right now? Be honest. Where on this scale would you fit? Okay. When should you test your software? Well, obviously, as time and experience grows, you'll tend to find you're more and more towards the bottom. Now, every 10 minutes, that's just silly. Okay. Every time a change or modification is made, well, that might be ideal, but that isn't always practical. So somewhere in the range near the bottom there would be good. Now, one thing I'll maybe mention right away, with a good testing framework, you can create groups of tests, or sometimes they're referred to as playlists, right? So what you might do is every time you make a change, you'd run a playlist of code that is nearby, most likely going to be affected by your change. And then less often, you might actually run all of your unit tests. So I'm warning you right now, on a large project, you can end up with literally thousands of unit tests, which can take quite a bit of time to run. Anyway, all right, just to get into some of the specifics. You have, believe it or not, created tests before, right? Even, if you had me as your teacher when you learned stored procedures, or whether it was somebody else, it wouldn't matter, right? Because in the curriculum, we had you write a test script, okay? A test to demonstrate that each stored procedure you wrote actually worked. And that's an example of a test. You're testing your software that way. Only makes sense, right? Now, the trouble with that is most tests that we programmers write, sometimes, you have the code itself, but where did you put that test? I wonder where that could be. Maybe it's lost, maybe you didn't even keep it, right? Well, you say to yourself, hey, that worked, so why should I have to worry about testing it again? But of course, time goes on, changes are made, and things do sometimes get broken. That's where most bugs come from, right? If you got it to work at first, perfect. That doesn't mean you never have to worry about it getting broken down the road, right? So some general principles about software development, and especially when we start coming to doing unit testing. This is another common phrase you might have heard. Write small, test small, right? Code should be written in bite-sized, digestible chunks, okay? Reasonable, but digestible chunks of code. And that way, the test itself can correspond. In fact, it's even more important that the test is small, that you just test one little bit of functionality at a time, right? If tests become large, then you have to create a unit test to check for bugs in your test, right? That would just be silly. So you'll find that unit tests are very, very small, designed to test usually one little bit of functionality at a time, okay? All right. Generally speaking, tests are usually based on use cases. So it might not even be you as a developer. Somebody else might sit down and make up a whole bunch of use cases that, okay, in these circumstances, this should be the result. Do a test to make sure we get it, right? And those are often called use cases. And of course, they should be easily repeatable, saved or stored so we don't lose them and lose track of where they are, right? So we can call them up quickly. And as I said, sometimes run a whole collection of tests at a time, right? Okay. That way we can retest every time we make a change that could affect the functionality of our code. So just a bit of history. I kind of like to include a little bit of comment about the history of how we got to where we're at with different things. So way back in 2005, Microsoft came out with a special version of Visual Studio. It was called the Visual Studio Test. Anyway, the test version. Can't remember the exact name now, come thinking. But anyway, it was the VSTS version, and it included a suite of tools to help you do unit testing, right? But even back then, there were already free open source solutions that worked with Visual Studio. A very popular one called NUnit, right? There's a whole NUnit org that's still active, still works today, dates back even earlier to 2002. A few years later, 2008, Visual Studio Professional above came with basically the Microsoft Test, MS Test, already built in to the Visual Studio itself. Just a note there that NUnit still works, still has free versions, okay? And another one that is worth looking at, in fact, if you're just starting and want to look at something other than the built-in MS Test, XUnit. It's a little more modern than NUnit, similar in its functionality and its approach. Okay. All right, so let's talk about best practices. Normally, we would create a unit test in a separate test project, right? We don't want to clutter up your actual code project, but it has to be able to work with it. So often it'll be added into the same solution with references, of course, to the actual project itself. And then that way it can be easily kind of tied in, work along beside your actual code, right? Now, quite often, all we really have to do is add the new test project to your current solution, right? And we'll show you how to do that in a few minutes if you're not sure already. Now, the attributes that we decorate our classes with in the unit testing framework, now these can vary a little bit depending on whether you're using NUnit, XUnit, or MS Test. These ones are specifically the ones we use in MS Test that we're going to demonstrate today and use throughout the course, right? So the actual class, okay, will be decorated as a test class, and then each method technically is what we often refer to as an individual unit test. We decorate that with test method. Optionally, there will be an initialize and a cleanup, okay, for each class, or for each method, and then class initialize and cleanup, right? In a larger, more complex system, you'll get into using all of these as well, especially if you get to the point where you start to use mock or fake objects, right? I mean, think about it. If your test involves testing functionality of how your classes interact, say, with the database, well, do you really want to spin up the database every time you want to do a unit test? Probably not if there's a way to avoid it, right? So what we'll often do is we'll create a mock of the database or a fake object, and it has an interface defined that just gives canned responses, right? But it's there really just to provide that interface that we can work up against as we test the logic in our own code, right? So anyway, time goes on and things get more and more interesting as they do, right? But let's get back to talking about an individual unit test, a test method, right? The general approach is laid out here. 3-step, arrange, act, and assert. Now, you can't make this fit every situation, but as a general approach, this is proven to be a good way to arrange your code. Sorry, I said the word arrange, but of course that's the first step. Basically, in the arrange section, okay, you arrange all the objects, instantiate classes if you need to, if it's a non-static class and so on, all the variables, prerequisites, and so on for the test. Then the act. You perform whatever action should result in the result you're after, right? Perform the test, basically. And finally, the third part of our 3-step process is assert, right? And this really is a way that we let the test runner, after all, we're going to look for a report when we're done. Okay, did the test pass or fail? What tests passed and failed and so on, right? So our assert object is usually used for that. It lets the test runner know the status of our test, right? I have a note there. When you first scaffold a new test, it will have assert.fail in place, right? Leave it there until you're finished with all the arranging and all the definition of the act and so on. You never want to change and get rid of assert fail because it should always be there just in case, right? It's a fallback, you might say. During development, you don't want to ever get a false positive, right? So that's a way to avoid that. Okay, let's just talk about some code samples. Now, let's just look at a real simple non-static class here, number fun, right? Where we have in our constructor, we pass in values for the first number and the second number. We're just working with integers here. This is just a real simple example. And then our class might have a property called biggest, where we determine with our values we were given for our first and second number, okay, what are we going to return? What's the biggest value? And that's what we end up returning. Looking at it, I think it looks logical, but how do we know? How can we determine it actually works, right? Well, somebody might sit down and say, well, let's make up some use cases where, the first number is given a value, the second number a value, and we expect, okay, a given result. and then maybe swap the values or try different values and so on and so forth. Maybe they might come up with a handful of use cases, even though you probably need a couple. But, they might come up with a whole bunch of them. Values close to each other, values far apart, et cetera, right? Anyway, so that's what a simple class, a non-static class here might look like. So what kind of a unit test might we create for this, right? Well, inside a test class, okay, we might have a method. Now, that method might be based on a particular use case, where we define we're going to use certain values and we expect a certain result, right? So we would arrange, okay, setting the values. Now, yeah, it's true. Like you could use fewer lines of code here, right? As we instantiate our number fun object here, right, and pass the values, I could just hard code the values there. I could just put in brackets 10, 5, right? You're doing it with variables defined and so on, instantiated values here. It's a good practice. It's not the end of the world if you bypass this, but remember, we want to make our tests clear and simple, easy to read and understand, right? So yeah, it's not a bad practice to go to all these extra steps here as well. And as part of the arrange, we usually define the expected result, or expected value in this case, of our test, right? Then the next step, act. Okay, well, that's just simply accessing our target object. By the way, we typically use, you'll find in most unit testing, the name target used for the class itself, okay, unless it's a static and it has its own name, right? Okay, so we ask for the biggest property, and that will actually carry out the logic inside of our class, and then that is really the act that's going to result in the result. Sorry, getting into silly puns here today. Okay, finally, we do an assert. Now, we'll talk more about the assert object itself. There's all kinds of built-in ways to assert, test, comparisons of different sorts, and so on. Okay, this is the most common, simple one, is assert are equal. And notice we aren't checking types here. We're just saying, are the values equal, right? And if the expected value, which we defined at the beginning to be 10, matches the actual value that was returned by the biggest property of our target object, then yay. All right, so our test runner will get a green light to saying, yes, the test passed, right? Simple as that. Now, I added a couple more slides here because I don't know why. I mean, you've done a lot of work with different kinds of classes in the past, but I often find that when we do these exercises, sometimes I'll use a static class and sometimes a non-static class. And for some reason, maybe it's because you're focused so much on the testing, but students forget, okay, how to work with the different kinds. So I've just got an example here. So here, let's say we're going to have our number fun class. I just use a slightly different name so I could have them in the same project. Static class, right? So it has a static method here called biggest, where we pass in a first number, a second number, again, still using integers, and we have the same kind of logic determining, are we going to return the first one or the second one, which is the biggest, right? So I just want to point out the difference then when you actually have this kind of a static class, when you write your test, obviously in the arrange, we don't instantiate it, right? Our references in our test project are sufficiently set up for the code project itself that all we have to do is refer to it, okay, numfun dot the biggest method, okay, and we pass our values for first and second. We'll get our actual value back. Of course, in the arrange, we define the expected value, and then our assert are equal is exactly the same. So I know this is getting nitpicky, but for some reason, even on tests and so on, students have often gotten a little bit confused as to different ways to handle the different types of classes. So that's why I thought I'd look at examples of both non-static and static here. All right, so let's talk a bit more about the assert class itself, right? As I said, it communicates success or failure back to the test runner. And basically, there's all kinds of methods that it has for checking test results. If they return true, then the test passes. If it's false, we get a red in the test runner, means the test failed, right? So as I said, one of the most common is simply assert are equal, but there are many overloads. I'm not going to try and list them all or talk about each one, okay? But even when you hit dot in your code and you see the list of all the overloads come up, you'll see all kinds of interesting ones. Maybe you're just going to check, is it an instance of a given type of class, right? Is it null? When you do are equal, you can also check that they're equal both in terms of the type of object and the value, right? And of course, assert fail is our fallback to say, if we hit this, it's a definite fail, right? So, like I say here, there are many types of tests possible using the assert class. As time goes on, you'll get a chance to try out more and more of them. Okay. Now, before we wrap up our discussion, I do want to mention there are some special cases, right? It's not just always a matter of comparing an expected result with an actual result, right? There's some special cases that come up. What if in your code you're testing that, hey, under certain conditions, we expect to get an exception raised? Wow, how are we going to test for that, right? The test isn't that we get a given result. The test is actually that things blow up, right? That we get an exception instead, okay? Well, then we'll talk about how we handle expected exception tests, right? When we're confirming that an exception is raised when it should be, right? Another special case is boundary testing. Perhaps there's a change of behavior happens, in a type of calculation or anything else at a certain point when conditions change, right? So what we have to do is we have to make sure that as close as reasonable to the boundary where this change of behavior happens, that we get the expected change of behavior, right? So we'll talk a bit more about that in a few minutes as well. Okay, first of all, exceptions. Well, there's two main approaches. We can use a try-catch around the assert, or we can use a special attribute. We can decorate the test with an expected exception attribute where we specify the type of exception we expect, okay? Basically, it's kind of like this tongue twister. You didn't fail to find the failure, right? We got the expected exception, okay? So we're specifying here that the correct result for a test is to get an exception, right? So, we're going to have test methods and properties that validate our input and so on. We can use test failure conditions, right, to make sure that that happens when it should, right? And then we can optionally specify the exact text of the exception, right? So it might be a out of bounds exception, but maybe there's more than one reason why things could be out of bounds or something like that, right? So we can actually check the exception message to make sure the actual message matches a particular a result that we're expecting and so on, right? Just a general note, just because you're checking for exceptions, we always want to have an assert fail somewhere in the test as well, so that, after you invoke the method that should raise the exception, well, what if it doesn't, right? Then, whether it's after the catch block or whatever, you want to make sure there's an assert fail in there so we avoid any false positives once again. Okay, so let's look at a couple examples. Let's suppose that in our num_fun class, we also had a property besides our biggest, where we simply do a division result of the first number divided by the second number, right? Okay, well, we all know that dividing by 0 is considered a no-no. Now, a wrinkle in the pudding here, I'm kind of mixing my metaphors there. What is it, a raisin in the pudding, a wrinkle? Anyway, you get the idea. Is that nowadays a lot of frameworks, including .NET, no longer actually raises an exception if you divide by 0 necessarily. Anyway, it depends on settings and so on. But anyway, let's continue with this example. All right. So in a case like that, where maybe we've added that division result property to our num_fun class, we might do an expected exception class like this, okay? We're going to have values, of course, where the second value or the denominator in our division will be 0, right? So we can say expected exception type of divide by 0 exception, right? We decorate that as an annotation right on the test method itself, okay? Then our range, we get our values in place for first and second. Because it's not a static, we have to instantiate our class, passing the values into the constructor, right? Our act is just a call for the division result of our target object, and that should be stored in actual. No, it actually shouldn't. What we should do is we should get an exception. So the assert fail is there, because if we get past that line in the act, right, and we go even further without an exception being raised, then that is a failure. You should not get that far, right? And this will actually show a green light, a pass in the test runner, right, as long as we do get the exception we're expecting. Okay, now just to show you the variation, if you didn't want to use this expected exception attribute, right, then you could use a try-catch as well, right? So this gives basically the exact same test result, right? Basically here, we'll make our range here. We'll have our first, our second. We instantiate our target using those values. Then in a try-catch, okay, that's the act will involve a try-catch where we do the access the division result property of our target object in the try. And of course, it should raise an exception. So it should hit our catch block, but we're being specific. This catch block is just for a divide by zero exception, right? If that's what we have, then we just return. That's it. No problem. That'll be counted as a pass of our unit test, right? Of course, after that, if we didn't get the exception, if the try-catch completes operation without going to the catch, then assert fail. You should not get that far. They're just showing you another way, the other alternate way to set up a expected exception. Now, you're going to get some chance to work on these expected exception tests as you work through the walkthrough I've assigned as your first tutorial here on this section. Okay, finally, boundary testing. We'll just discuss this, right? Later on, we'll do some work with it. But for now, this is where we're talking about that change of behavior. So it could be all different kinds of behaviors. As long as you can test for it, you can, you can do this, right? A simple example I can think of. Let's say that you pay a commission based on the amount of a sale, right? And if it's over $100 the sale, you pay a given commission rate, maybe a higher commission, than if it's less than 100. Okay, if it's exactly 100, you pay the higher rate, right? So that's all clearly defined in your employee manual or whatever, right? So there's a change of behavior happens at that boundary. So we have to create unit tests around the boundary, right? Okay. So one of the things about boundary testing is you have to be reasonable in how much above or below the boundary you are going to test, okay? You can say, well, I'm going to test $1 million, right? Well, okay, yep, you might determine that it's above 100, so you should use a certain commission rate. There you go, you did a unit test. Is that reasonable? I would say no, right? That's nowhere near the boundary. There's very little value in that as a unit test, right? Okay, so you got to be reasonable in how much above and below you go. So now, here's an example. Integer values are easy. Let's say, we only worried about the dollar and not the pennies, right? So let's say at 10, you expect one behavior, at 9, a different behavior. Pretty easy. You have 2 unit tests, one at 9 and one at 10. Boom. And you make sure the behavior is different or the expected behavior as you go across the boundary, right? There you go. Okay. Floating point numbers are a little trickier, right? Double, decimal, any kind of floating point number. So as a general rule, what we do is we look at the number of significant digits that you're using in the required output. And as a rule of thumb, we often go to 1/10 of a significant digit, right? 1/10 of whatever the significant digits are that are being used for output to the screen or whatever, right? So for example, if we go back to our commission rate, okay, if it's $100 or above, right? So if we're rounding our currency values to the nearest penny, okay? So if there's that change of behavior at $100, then, you would probably go 1/10 of a penny, okay, below and use $99.99.9, right, as the test for the lower boundary. And because the behavior at 100 is defined to be the same as 100 or above, then you could use 100 for the upper boundary. All right, so a little practice with that. But, again, on tests, that's something students often, they use something way below and way above. And yeah, it might technically pass, but you're not going to get full marks unless you're reasonable in how close you define your boundary testing. Okay, well, that wraps up our discussion. Let's get into some examples.